Hello my friends, and welcome back to the Wow Machine channel. The explosive demolition of the South Bank gas holder and junction houses was executed with precision engineering and controlled sequencing. Prior to detonation, structural assessments were carried out to identify key load-bearing points. Explosive charges were strategically positioned within the holder's framework and supporting junction structures to ensure collapse inward, minimizing debris scatter. Safety perimeters and exclusion zones were established, with monitoring teams overseeing vibration and dust levels. At ignition, synchronized blasts severed critical connections, allowing gravity to dictate a controlled implosion. The demolition cleared the site efficiently, preparing the area for redevelopment while maintaining strict safety and environmental compliance. The ZX1800K crane, equipped with a two-piece boom measuring 53 meters in length, represents a highly specialized lifting system designed for heavy construction and infrastructure projects. This configuration is developed to achieve both height and reach, while maintaining stability and efficiency during demanding operations. The boom is manufactured as a modular two-piece system which allows for flexible assembly depending on project requirements. Each segment is fabricated from high-strength steel, engineered with lattice or box-type reinforcement to optimize load distribution. When assembled, the combined length of 53 meters provides a wide working radius, enabling operators to access elevated or distant lifting points without relocating the base machine. This versatility reduces downtime on site and maximizes operational efficiency. The installation of the two-piece boom begins with the careful positioning of the base section onto the crane body. Hydraulic pins and locking mechanisms secure the connection, ensuring rigidity and safety. The second section is then lifted into position, aligned, and fixed using precision-engineered joints. During this process, monitoring instruments and torque control systems are employed to guarantee proper alignment and load-bearing integrity. Once the boom is fully extended, counterweights are adjusted to balance the crane's center of gravity. In operation, the ZX1800K utilizes advanced hydraulic systems to provide smooth, precise movement across the full boom length. Operators can execute complex lifting sequences with high accuracy, supported by load monitoring sensors and automated safety controls. These systems continuously track stress, angle, and load distribution, issuing alerts if working limits are approached. The two-piece configuration also minimizes structural flexing, which is critical when lifting heavy components such as prefabricated beams, steel girders, or precast concrete elements. The extended reach of 53 meters enables the ZX1800K to perform tasks such as bridge construction, high-rise assembly, and installation of large industrial structures. On confined urban sites, the long boom reduces the need to reposition equipment, saving both time and labor. Additionally, the modular design allows the boom to be disassembled into manageable sections for easier transport between projects. From a maintenance perspective, the ZX1800K boom system is designed with accessibility in mind. Welded seams, joints, and hydraulic connections are reinforced and coated for corrosion resistance, ensuring long service life under heavy-duty conditions. Regular inspection points are integrated into the design, enabling rapid checks of load pins, cables, and hydraulic hoses. Safety is central to the crane's operation. The long two-piece boom is supported by an array of stability controls, including outrigger systems, electronic load indicators, and emergency stop functions. Operators benefit from a clear interface in the control cabin, providing real-time feedback on boom angle, extension, and load status. These features ensure that even at maximum length, the crane operates within secure parameters. In summary, the ZX1800K with its 53-meter two-piece boom is a high-performance lifting solution tailored to the most challenging construction projects. Its modular assembly, robust structural design, and advanced control systems provide a combination of reach, strength, and precision. By enabling safe handling of heavy materials at extended heights and distances, this crane plays a crucial role in modern infrastructure development, offering both technical reliability and operational efficiency. Iron ore extraction in South Australia is carried out through a combination of open-pit mining, ore handling, beneficiation, and export logistics. Operations are primarily located in the Middleback Ranges near Whyalla and the southern iron deposits near Coober Pedy. At the Middleback Ranges, mining is performed in several large pits using drilling, blasting, and truck shovel fleets. Excavators and haul trucks transport ore to fixed and mobile crushers, where it is reduced in size for further processing. Screening plants separate lump and fines, while beneficiation plants upgrade lower-grade ore through crushing, grinding, and magnetic separation. A magnetite concentrator produces slurry for pelletizing. The South Middleback operations consist of 5 active pits supported by multiple ore handling facilities. In the North Middleback area, Iron Barron and Iron Knob sites operate with upgraded pits, mobile crushers, and beneficiation plants. These facilities recover ore efficiently while reclaiming older stockpiles. The Southern Iron operations include the Peculiar Knob Direct Shipping Ore Project. High-grade hematite is mined, crushed, and transported without intensive beneficiation, enabling rapid delivery to market. Additional resources at Hawks Nest and Windy Valley provide future capacity. Material handling and logistics are fully integrated. Ore from mining areas is moved by a dedicated private rail system to the Whyalla steelworks and port facilities. The port infrastructure consists of storage pockets, conveyor systems, and ship loaders equipped with dust extraction units. Large capesize vessels, up to 170,000 tons capacity, are loaded offshore using a transshipping system. In parallel, a pelletizing facility operates within the Whyalla steelworks. Magnetite slurry is delivered via underground pipeline from concentrators. then processed through filtering, drying, balling, and induration to form uniform pellets. These are supplied to blast furnaces as feedstock or exported. Across all operations, mining machinery such as hydraulic excavators, large-capacity haul trucks, crushers, conveyors, and beneficiation equipment form the backbone of production. Continuous exploration programs ensure long-term resource availability, while dust suppression systems, rail integration, and offshore loading technologies maintain operational efficiency. The overall process, from drilling and blasting through crushing, beneficiation, rail transport, pelletizing, and shipping, ensures high-volume iron ore production and consistent export capability. The piling process is a critical operation in foundation construction, particularly when working in unstable, sandy, or silty soils with a high water content. One common method applied in such conditions is continuous flight auger (CFA) piling, which ensures stability during drilling and concrete placement. The operation begins with the positioning of a rotary piling rig fitted with a hollow stem continuous flight auger. The auger is drilled into the ground to the required depth while simultaneously removing soil through its flights. Unlike open-hole methods, the auger itself supports the surrounding soil, preventing collapse during drilling. Once the auger reaches the design depth, the concreting stage begins. A high-pressure concrete pump is connected to a large-diameter delivery hose which feeds into the top of the hollow auger. Concrete is then pumped down the stem and discharged at the base of the bore. As the auger is gradually withdrawn, fresh concrete fills the void created by the auger, while simultaneously occupying the flights, ensuring the hole remains filled at all times. This controlled process eliminates the risk of soil collapse or groundwater ingress into the bore. The excess concrete that appears as slurry at the auger tip is simply displaced material, indicating that the bore is fully filled. After the auger is completely extracted and the concrete column formed, a prefabricated reinforcement cage is lowered directly into the still fluid concrete. The cage insertion must be carefully timed, as the concrete should remain workable to allow proper placement. The reinforcement provides structural strength, enabling the pile to carry both compressive and bending loads. This method is particularly efficient because it combines excavation and concreting into a single continuous operation. It is the preferred technique for sites with loose, wet, or GR. In summary, CFA piling relies on the interaction of heavy drilling equipment, a concrete pump system, and reinforcement placement. The auger maintains bore stability. The pumped concrete ensures immediate filling as the auger is withdrawn, and the reinforcement completes the structural element. The process allows for reliable deep foundation construction in challenging ground conditions while minimizing A seasoned excavator operator understands not just how to control the machine, but also how rocks behave under pressure, impact, and rolling motion. Instead of rushing or forcing the excavator to lift beyond its limits, the operator uses finesse, carefully positioning the bucket, adjusting hydraulic pressure, and applying gradual rolling force. This avoids damaging the machine and reduces the risk of uncontrolled rock movement. Positioning the excavator on firm, level ground. Stability is essential because the operation involves repeated pushing forces against heavy material. The operator places the bucket teeth or cutting edge against the side of the rock and applies steady pressure to start the rolling movement. The goal is not to dislodge the stone in one motion, but to keep it turning over itself. This rolling action directs the weight downward and avoids placing excessive stress on the boom or hydraulic system. As the boulder rolls, the impact with the ground or contact with other rocks often creates natural fractures. By carefully pressing with the bucket at weak points, the operator can encourage cracks to widen until the stone splits into smaller, more manageable sections. This technique eliminates the need for blasting or external braking equipment in many cases. Once fractured, the operator continues to roll each smaller piece toward the disposal area. If the worksite includes a ravine or designated dumping slope, the excavator can guide each block to the edge and control its descent. Safety is paramount. The machine must always keep the bucket between itself and the rock to prevent rebound, and no workers should remain within the rolling path. This method demonstrates how skilled handling of the bucket transforms the excavator into a versatile tool for rock management, reducing risks and improving efficiency in difficult terrain. In December 2022, the HS2 Marston Box project achieved the world's longest box bridge slide, enabling the high-speed rail line to cross the M42 motorway in Warwickshire. The operation involved the controlled movement of a 12,600-ton bridge structure, designed to be slid into place with minimal disruption to motorway traffic. The sliding mechanism was engineered and executed by Freycinet, in collaboration with Balfour Beatty Vinci, BBV. The system relied on the auto-ripage technique, a specialized heavy handling method that employs hydraulic jacks and a guiding raft. This system allowed the massive box structure to be incrementally pushed along a prepared sliding surface with high precision and stability. The operation commenced on the 24th of December, progressing continuously over the Christmas period. With a sliding speed of approximately 4 meters per hour, the box advanced steadily over a total distance of 163 meters. The movement was completed in under 36 hours, significantly faster than anticipated. Upon reaching its final position, the bridge provided the structural base for the railway to pass over the motorway. The efficiency of the process enabled the M42 to be reopened a full day earlier than scheduled, minimizing traffic disruption and marking a milestone in large-scale civil engineering. The construction of the CEVA tunnel in France demonstrates the precision and complexity of modern underground engineering. The process begins with the creation of retaining walls adapted to the soil and water conditions. In humid zones, diaphragm walls, known as parois moulées, are formed by deep excavation using specialized grabs or hydromills. These reinforced concrete walls stabilize the ground and prevent water infiltration. In drier sections, a different system is used: parois parisiennes. These consist of soldier piles and timber or concrete lagging, providing structural support with a lighter, more economical design suited for dry soils. Once the retaining structures are in place, engineers proceed to the creation of the roof. A reinforced concrete slab is poured at surface level, establishing the permanent ceiling of the tunnel. This approach allows traffic and daily activity above to continue undisturbed while excavation continues safely below. The technique, known as top-down construction, minimizes disruption to the surrounding environment. With the roof in position, excavation begins inside the protected volume. This method, called terrassement en taupe, or mole-style excavation, involves carefully removing soil beneath the slab. The process advances in controlled stages, ensuring stability while gradually revealing the full tunnel cavity. Simultaneously, open sections are excavated to form access ramps, creating direct connections between the surface and underground works. Managing groundwater is essential. To control the flow of the water table, siphons are installed. These drainage systems ensure the groundwater is safely diverted away from the tunnel, preventing hydrostatic pressure from compromising the structure. Finally, the base slab or radier is constructed. This massive reinforced concrete foundation becomes the structural floor of the tunnel and will eventually support the railway tracks. Precision in this stage guarantees both durability and the smooth integration of rail systems. Through the coordinated use of diaphragm walls, Parisian walls, roof slab installation, careful underground excavation, groundwater management, and final base slab construction, the CEVA tunnel emerges as a technical achievement. Each phase reflects a balance between engineering efficiency, environmental control, and structural safety, showcasing the ingenuity of contemporary tunnel building in complex urban and geological conditions. To install a 54-inch PVC pipe, the process begins with careful trench excavation following the design drawings. The trench base is prepared with a compacted bedding layer to provide continuous support. Each pipe section is lifted and lowered into position using cranes or excavators fitted with spreader bars and slings to avoid damage. Before joining, the bell and spigot ends are thoroughly cleaned and lubricated to ensure a watertight connection. The spigot is then aligned and pushed into the bell using mechanical force, securing the joint. Once in place, haunching material is packed and compacted around the lower half of the pipe to stabilize it. Backfilling is carried out in controlled layers, with compaction at each stage to maintain alignment and prevent settlement. Finally, inspections and pressure testing confirm that the pipeline is correctly installed and fully operational. Cement production begins with the extraction of raw materials such as limestone, clay, and marl from quarries. These materials are crushed into smaller pieces and proportioned with additives like sand or iron ore to meet the desired chemical composition. The blended mix is then ground to a fine raw meal. After blending, the raw meal is preheated and enters a rotary kiln at approximately 400 to 500 degrees Celsius, where chemical reactions produce clinker through calcination and sintering. The red-hot clinker is quickly cooled, then ground with gypsum and sometimes other additives in mills until it forms a fine powder. Gypsum regulates setting time. Finally, the cement is stored in silos and packaged or shipped in bulk for use in concrete or mortar.